that. I'm opening the lecture so that we can share, I can share my screen.
وعليكم السلام دكتور مشكور.
Sorry, I was talking while muted.
عليكم السلام دكتور حياك الله.
I'll share my screen soon, but I'm opening the files. So last time we were talking about the environmental impact of power generation, especially from fossil fuels. And we introduced quickly the carbon capture and sequestration to reduce the global warming due to the emission of CO2 or carbon dioxide from burning or combustion of fossil fuels. This is the main concern from power generation is the emissions. Of course, the emission of carbon dioxide is a main contribution to global warming, but there are other gas emission like nitrogen oxides or sulfur oxide due to the, in some cases, high temperature to produce NOx or nitrogen oxides, and also some contamination of sulfur with the fuel, either natural gas or. Again, I decided to admit all. So some people are waiting. I need to see the teams, how many we are. Now we are 21, including Dr. Antar, myself. Sorry, Dr. Antar, for a quick question. How many students we are in the class? 22?
We are 21 students.
Oh, 21. So we are remaining with 2, I think, because so far we have 21, including Dr. Antar and myself. Okay. I tried to link each lecture with the word sustainability because you raised an important question. What is the relation to sustainability, which is your main program, master program? It's about sustainability. Again, to remind you and myself that sustainability means continuity of using the fuel source. We can do this as we know, either reduce using it by finding alternative energy like the renewable energy instead of using the fossil fuel all the time, or reduce the use of it by increasing the efficiency, because if we increase the efficiency, we mean for the same power needed, we are going to burn less fuel. Also, this not only on the production state that we improve the efficiency of our power plant, but remember also we can increase the efficiency of our consumer side. For example, air conditioning that use most of the electricity produced, 70% of electricity produced goes in houses for air conditioning. So if we raise the efficiency of our air conditioning, it's going to use less energy, so will represent less load on the power plant. So consequently, we are going to satisfy this load with less power or less fuel. So I think this, I'll keep reminding you and myself, what is the relation between our topic and the sustainability. For carbon sequestration, is a key long-term sustainable use of fossil fuel. Why? Because now most of the countries agreed to apply constraints on the emission of CO2 due to the global warming. And in 1994, there was a measurement that there is a 7 gigaton mark reached, 6 gigaton reached in 1994. Within 1 year, we reached 7 gigaton or approach it. So countries even putting laws to increase the efficiency or to put a percent of the power generation by renewable energy. I think in US, they apply now that any power plant, because power plant to production, there is private companies. So any private company produce electricity, they have to produce a share of about 20% from renewable energy. Or raise the, yes.
I have general question about the allowed emissions to the harm the environment. Is it true that some countries they exceed their يعني يتعدون الحد المسموح فيه بس يكونون they are utilizing other countries allowable limits?
Yes, they buy it, as
They
we
buy
said.
it, right?
They buy it. We are going to touch something like this today. Even people like you or me, we can, because they put the carbon taxes on the consumer side, you know. Now they are thinking to apply it to producer side of energy.
So if I'm allowed, for example, 10, and I know that I will exceed, I will reach 15, I can buy from a different country.
I think the credit, if they have some measures that they have less carbon emission, then they can sell their credit. I think we touched this last class, and there was the example. I said I'll solve it next class because of the time. But I think that we are going to solve it with other question in the help session, because today lecture is having some type of the thoughts you are raising, plus some numerical numbers or examples. That is like the last one, energy auditing. If you have your plant, like the last example, we solved it in the help session about if you have this much of energy produced, 7 million gigaton hour, gigawatt hour per year, how much tonnage of CO2 produced, we'll have something like this, how much carbon dioxide you can sequestrate and so on. So the idea is clear in your mind that there are taxes now and constraint restriction on emissions. So if we didn't find a solution to get rid of this CO2, we are going to limit the amount of fossil fuel we are burning. So people might be with time not willing to buy oil and burn it. They will look for other option that doesn't produce CO2. But if you have a way to sequestrate or to capture this CO2 from your exhaust or from your plant, then still you can burn more fossil fuel, which I don't encourage myself, but still you are not paying these taxes, or you are not exposed to the penalties that will be imposed by all governments later. So to have your power generation is clean, or let us say emission free, there are ways that can help you to do this: burn fossil fuel and clean your exhaust. So one of these ways is sequestration, carbon sequestration, or actually separate carbon dioxide from the exhaust and store it somewhere. So we have two main categories for carbon sequestration. One is the direct or active sequestration. This will be whatever human can control to separate CO2 from the exhaust. I mean, from let us say in the exhaust, if you burn a fuel with air, we have mainly nitrogen in the exhaust and CO2 plus some water vapor. So how to get rid to have CO2 alone? Because we need just to compress the CO2 and dump it under the ground or something. So this will consume energy. So I don't want to actually sequestrate nitrogen. Nitrogen is not harmful. It's part of the normal atmosphere. So why should I take all the exhaust while most of it nitrogen and pay the energy to compress it and sequestrate it in the ground in reservoirs, as we will discuss. So separation is important. Of course, it will use some energy, but it will save the compression energy at the end. Indirect sequestration, that is actually doesn't need the human control or interference. It's a natural process that takes CO2 by living organisms like plants or forests, so that accumulates CO2 at the greater rate than would otherwise have occurred. Actually, these having plants, that it is known that it takes CO2 with photosynthesis and convert it into hydrocarbon or glucose. This is a very important process for human, since it takes the CO2 that bother all of us and produce oxygen that all of us are happy with. But I mean, how this is being done, what are some numbers that a tree can do, how much CO2 it can absorb. This we are going to see some examples on that. Indirect sequestration is presently carried out using forests, as we said. Experimental work is also underway to use a smaller organism that have photosynthesis in order to sequestrate carbon. And researchers have considered techniques to accelerate the uptake of CO2 in oceans by altering the chemical balance. For example, filterizing the ocean, they put some iron or nitrogen. So when they put the CO2, they can react. And actually, this is now because you alter the, the biological scene in the ocean. They are stopping it or trying to find more safe ways. But now, because it has negative effect on the marine, so they stop it. But forest-based sequestration, this is what someone was asking. Now, if we produce more CO2, now you can pay for countries in Africa or in the places where you have forests, like in Brazil or so, to help growing more forest to absorb CO2. I think this is going on in US especially. So forest-based sequestration can be carried out either using afforestation forest or planting new forest, especially over the last few decades, many of the forests have been either deteriorated or cut or removed for planting or normal agriculture. So what happened that you need to produce or to have to plant more forests, and this is will cost you some money and also will cost you some energy, because you need to use fuel for transportation, for preparing the land. And actually this plantation for large lands you will use some energy. You might burn some fossil fuel to run your vehicles or so. So at the end, if you have a project for forestation, you need to see what is the net CO2 sequestration, because the plants will take time while you take care of it until it grow and become matured. All this time it is absorbing CO2, but still you are paying, some effort and using transportation, producing also CO2. So the net calculation of CO2, how much this forest will produce CO2, will sequestrate CO2, and how much you burn fuel and produce CO2, you as a project manager or a team, you have to calculate the net CO2 absorption to see how much it is saved. Actually, the photosynthesis, this process, we learn about it since prep years and primary years in our schools, so that we know that plants take light and convert it into use the energy in the light to make a chemical reaction like this. You take CO2 plus H2O from the ground, some energy from the light, and the plant to produce glucose like C6H12O2 plus some oxygen. And this is the chemical energy, chemical balance equation. So how much energy needed by the plant to produce 1 mole of or to absorb 1 mole of CO2. Let us see the numbers. Numbers here is from your book. It's about 9.5, 10 to the power minus 19 joule per molecule, 1 molecule of CO2. You might look at the number here. You find very small to produce or to absorb, sorry, 1 molecule of CO2. Actually, if you look at how much energy coming from the sun light incident on the Earth every day, you'll find it's a huge number. But why not all the CO2 produced by human activity? Why not is absorbed? It is not absorbed by the forest or by the plants. Because actually many reasons, I'm listing here some of it. Plant trees leaves absorb only light waves in visible light range. I mean, the infrared or the ultraviolet lights or waves that have also energy are not absorbed by the plant's leaves. Also, more important that the surface of the plant or whatever the green area you have, that you are hoping that absorb the CO2 around it. The light, the surface is not uniform. It has ups and downs. Also, leaves are not organized in uniform way. So most of the light actually go to the ground instead of incident over the leaves or absorbed by the leaves, and most of it reflected far away. So we don't take much from this energy in the light. So by the end, so you have the sequestration by trees is from 1 to 2 kilogram of CO2 sequestrated per meter square per year. And the tree can keep this rate between 1 to 2 kilogram CO2 absorption for each meter square from its surface per year, 1 or 2 kilogram per meter square per year. But this will continue for 20, 30 years if you have planted one tree. So majority is lost of, I mean, not absorbed fully by the plant. And then there is here a quick example. That's why we don't use all, we cannot utilize all the light incident on the ground to sequestrated by green trees or so. He is giving a given species of trees, a kind of a tree that can sequestrate 2 kilograms of CO2 per year per meter square of a planted area in growing condition where average sunlight make available 100 watt per meter square. Even I think this is a sort of a good number in a sunny place, is taking into account that night and day. Also, don't forget that we have the day is having also nights and seasonal cycles where we have the weather vary and have clouds in winter. So he's asking, but this is not the question. The question is how much energy is required to convert the CO2 via photosynthesis into carbon that is sequestrated. I mean, it will be glucose and it will be used in the tree to have to grow, and at the end it is wood, you know. And what percentage of annual available energy is used? So the available energy, if we have 100 watt per meter square, and then we have this per year, so how we convert this number into energy by multiplying by the number of hours of the year. But the 2 kilograms of CO2, how many moles are there? How many molecules? We know that 1 meter cube of any gas include Avogadro's number of molecules. Yes, please.
This 100 watt is directly from the sun, or what?
Yes, yeah.
Okay.
He's saying where average sunlight makes available 100 watt per meter square. Okay, so we need to know, as we sit here, each molecule of CO2 to absorb it, you need 9.47 times 10 to the power minus 19 joule per molecule. So if we have 2 kilograms of CO2, how many molecules it have? We know that by volume, 1 meter cube has a Avogadro's number of molecules, which is 6.022 times 10 to the power 23 molecules. But we need to know in 2 kilograms how many moles we have. So we divide the 2 kilogram, this mass, by the atomic number of CO2, which is 44. You know how to calculate the atomic number or for any chemical composition like CO2. We have C, it has 12 atomic number, and oxygen have 16. So O2 means 2 times 16 is 32 plus 12 for carbon, then it is 44 gram per gram mole, so or kilogram per kilomole. Then 2 kilogram divided by 44, how much moles we have, and then we multiply. This gave us a number of, multiplied by Avogadro's number, give us a number of moles we have. Then if we have this number of moles at 2.74 times 10 to the power 25 molecules, then we multiply by the energy required for 1 mole of CO2 to absorb. It gives us 2.59 10 to the power 7 joule. This is or 25.9 megajoule. This is to absorb the 2 kilogram per year. To absorb the 2 kilogram per year, you need 25.9 megajoule. But how much energy come to you per year? We have 100 joule watt per meter square. Assume we are going to take, but we have per year, because he said this is the average per meter square. So the average mean he take day and night, he take average. We know that half of the day we don't have sun, but he is giving the average number, that 100 watt per meter square. So we'll see how many per meter square, how much joules, how many joules. We multiply by the hour, is 3,600 seconds per hour, and multiplied by how many hours per year. It is 8,760 hours per year. So per year you have the incident radiation from light is about 3.15 10 to the power 9 joule per year coming energy. But you need only from it 25.9 megajoule. We divide the number. So this sequestration of 2 kilogram of CO2 by these 3 per year is 0.8%. Hello? Hello? Any question? So if you are talking something outside the class, please mute yourself. Shall I continue?
Yes, Doctor.
Yes.
So this tree is utilizing less than 1% of the light coming to it. So as we know that this indirect sequestration or helping planting the forest is now being forced by government seeking to meet carbon emission reduction, and the non-governmental organization that help or administer frustration on behalf of institutional and individual. Radial rates of sequestration may be on the order of 1 to 3 kilogram of CO2 per meter square per year. We said 1 to 2, but maybe with some more activities, we can increase it to 3 during the growth period. The growth period when the plant is growing, but when the tree is matured and it will not consume as much. So that's why average is between 1 and 2. So the cost actually is around, if you have already a forest, it might be $1 per ton of CO2 sequestration. But if you are going to plant the forest yourself and you spend more money on it, then the rate of $20 to $30 per ton, which is really in also low side to sequestrate 1,000 kilogram of CO2. You need between let us say between $1 and $30. This is still in the cheap side. But also planting more forest will help the ecosystem from different angles. You can read about this, the benefit of forest to the nature, or to the habitat, that even sometime during floods, these trees or forests even might slow down the flooding and reduce its side effects. Actually, a new technique to offset CO2 caused by individual is that you pay some money, like your colleague who asked it at the beginning, that the individual or a plant that produce CO2, and they can pay money or buy it from other country in a form of paying them money to help growing forest, because growing forest might not be suitable in all land. Like here in our Middle East, we have most of our land a desert. We don't have enough water to sink to plant the desert. We need water. Then we go to Dr. Antar asking for desalination, and he will cost us a lot unless he invent new things to desalinate water cheaply. But now it is the sort of cost. So you pay to other countries like in the near the equator or so to grow more forest. So this example, next example, it's example 7.2 in your book, giving an idea that a family that produce 400 kilowatt hour per month of electricity and wishes to buy sequestration offset from an organization that plants trees in Africa. The organization charged $90 per tree, right? $19, sorry, per tree to plant it, and estimate that each tree will, on average, absorb about 730 kilogram of CO2 over its lifetime. Its lifetime about 20, let us say 20 years, it's 20 to 30, let us say 20 years. Electricity consumed emits CO2 at the 2003 classification by New York State average rate based on the energy mix. Given there is a table that depends on what fuel you are using, what source of energy, then we can estimate how much CO2 is produced per kilowatt hour. So if this family is consuming 400 kilowatt hour, what is the CO2 emission for each kilowatt hour they are consuming? Consumers allow, the organization allow consumer to purchase a fraction of a tree. If we have 2.5 or 1.5, so it's okay. They pay money. They don't really buy a tree. How much must the family spend to offset emission of 1 year? This example is similar if you have an electric company produce electricity and you exceeded the credit you have for or allowed, or the limits you allowed to you. Suppose each tree is planted in a stand of trees where it covers a cross-sectional area of 6 meters diameter and takes 20 years to mature. What is the rate of CO2 sequestration in kilogram per meter square per year? Let us see, it's a sort of energy audit. You just trace the numbers and make your calculation and estimation. First, we need to know how much CO2 this family produce per year, and then each tree, how much it absorb per year. Then we see how many trees they want. And the cost of one tree is $19. So this is the story of that example. Here, the energy mix production in US for New York, from nuclear, they have 28%, but nuclear doesn't produce CO2, and this one advantage of nuclear power plant. Hydro, like waterfalls and other thing, 18%, but has no contribution to CO2. Gas and the other fossil fuels, they produce 0.42 CO2, ton of CO2 per megawatt hour, or 0.42 kilogram of CO2 per kilowatt hour. And its share of production is 19% from natural gas, let us say. Other fossil fuel, 33%, and it produced 0.77 kilogram of CO2 per kilowatt hour, or ton of CO2 per megawatt hour. What is this table useful to us actually? If assume we are living in New York City, then this is the sources of power generation used by the companies in US from nuclear, hydro, gas, and other fossil. At home, at my home, it comes to me electricity. I don't know from where, what is the source. Is this nuclear, or it is hydro, or gas? I'm buying it from X company that has this combination. So my house contribution to CO2 emission is 19% if it is coming from gas, and 33% if it is coming from other fossil fuels like coal, oil, whatever, and 0% from other sources. So if I want to see how much my contribution to CO2, then it is, I assume that 19% from whatever coming to me, the source was gas, or it was other fossil fuel. So my contribution at home is 0.19 from gas time how much kilogram per of CO2 per kilowatt hour, or ton of CO2 per megawatt hour is 0.42 if it is gas, and 0.77 if it is other fuels. But the share is 0.33. So the total, when I combine these numbers, I will have my house is producing or contributing by consuming this electricity. My house is contributing 0.33 ton of CO2 per megawatt hour I'm using. But we are using the annual consumption is 400 kilowatt hour per month, and per year isn't. It is 400. This is the question. 400 kilowatt per month. We multiply this by 12, so it will be 4,800 kilowatt hour per year, or it is 4.8 megawatt hour per year, right? Then the amount of electricity that produce CO2, we have it 0.33 ton of CO2 per megawatt hour, and we are consuming 4.8. So multiply these two numbers, give us 1.6 ton emitted per year. So 1.6 ton, how much the tree is absorbing per year? It is 0.73 ton of CO2 during lifetime, 0.73 ton of CO2 in its lifetime of 20 years. So if we are producing, this is what we are producing, 1.6 ton emitted. So we need, we divide 1.6 ton divided by 0.73. We got 2.2, we need 2.2 trees. And each tree cost $19. So we have to pay to this country in Africa through the organization that is stated in New York, $41.68. Now he has an asking a question, how much is the rate of CO2 absorbed by the tree over 20 years? So we have it absorbed per 20 years, its lifetime 730 kilogram over 20 years. But what is the area? It has a diameter of 6 meters. So pi r square, this is the radius. This is P is pi r square, which is 6/2, all squared. The area is 28.3. So per year, it absorbs 730 kilogram over 20 years. So I divide by 20. So if I need it per meter square, I divide by the area or outer area, which he said it has covered the projected area. It has a diameter of 6 meters. This is the, of course, imaginary diameter as if it is cylindrical in shape or the circle. So this is how many kilogram of CO2 per meter square per year is absorbed by this type of tree in I will buy in Africa to offset my contribution to CO2 emission. Now, there are, for this indirect or planting the trees and this, what is the future of it? Actually, to wrap up or to summarize, we know it is clear that indirect sequestration is straightforward, economically is viable option for sequestration. Even if your country doesn't have forest, you can help another country. I think with time, because the globe becoming like one village, and we are affecting each other, especially the emission, it's not limited to one country. I remember maybe 10, 15 years back, Europe was thinking to buy electricity from Middle East instead of buying the fuel and burning there in their power plant through connecting the electric grid. So if we, for example, produce electricity here because we have fuel and then export the electricity, this doesn't prevent the emission that go to Europe because it's produced here, but spread everywhere, right? So there are some challenges. So the world now should help each other. This is what I want to say from that example. So competition of integrity of planting, we need to, these are issues. If there is competition and the integrity issue of a planting organization, also we need to maintain the forest in equilibrium over the long term, increasing cost of sequestration over time. Why we should, I mean, like this family that pay $19 per tree, this will not be always fixed, because now many of the forests are being cut for the human use. So the land is becoming limited, and we need to cultivate or plant more. So also uncertainty about effect of the global warming, for example, or weather variation on the forest. What will happen? Some people are saying if the globe temperature increases, so it will affect the ground and make the tree produce or the area of the forest to produce more CO2 than it absorbs, because actually the tree is a living creature. So it take light and CO2 to make its food in the photosynthesis process, but also when it breathes to burn the food to have the energy to grow and build the cells, and just it also consume oxygen and produce CO2. And usually this happen at night, you know, this from our primary education. So any tree like produce CO2 at night and absorb CO2 in the daytime where there is sunlight. But the net is absorbing more CO2 than it uses. But they're saying with global warming, this will, the CO2 produced by the forest will increase. But the others say that no, when there is more warm in the ground, maybe the under tree, like grass and other plants will grow better. It will find the more chance to grow, and then it will help in absorbing more CO2. These debatable things are not clear because it needs research. You need to record data. Before our current time, we don't have enough data recorded to trace this. I will stop here for the first session, and I would like to see if you have any questions. Otherwise, I'll start this. Yes, please.
Yeah, last sessions we take some thermodynamics lessons and Brighton cycle and Rankine cycle. So now we jump to carbon sequestration, which
We
is
didn't jump. We didn't jump. Actually, last time we talked about combustion techniques that will help us to separate the CO2 because, as I said, your main program is sustainable energy, right? That's why we have this course that is talk about sustainability from different angle. One is increasing the efficiency of the production of energy or conversion of energy from conventional power plant, which is more than 80% of the power produced is from fossil fuel. I mean, here in Saudi Arabia, so far it is almost 100%. You produce energy from burning natural gas and oil, isn't it? So we cannot focus now on renewable energy. Of course, we are preparing you for the future, but nowadays you have to do something what is on ground. If you have almost 99% of the energy produced in Saudi Arabia is from fossil fuel, and actually this fossil fuel is the main source of income to our country. So we have to use it efficiently. We have to save it for other products. And if we save 1 liter of oil, this means that as if we produced one new or we discovered 1 new liter of oil, isn't it? In our fields, oil fields. So mean here sustainability, we should talk about how we convert the energy using fossil fuel, and mainly by first combustion, burning it. We talk about how the thermal cycle, which is the Brighton cycle, Rankine cycle, how to improve its efficiency, because improving the efficiency save fuel as we done last class. But now the main, one of the main process in the conversion of fossil fuel energy into electricity, that it's easy to distribute, easy to use, it's clean, all this. But at the beginning, we are burning fuel, isn't it? So how to make the burning the fuel or the whole process of burning fuel, converting it to electricity, we make it more clean. Why we need to do this? Because we need to reduce the emission of CO2 that will create or contribute to global warming. Why we are worried about this? Because there will be laws to force you not to use the fossil fuel if your carbon dioxide emission is above these limits. So you need to look, if I want to continue, not me, I want the world to continue using fossil fuel. Why? Because I'm selling it to them. We need to do this for a long time. We need to sustain selling the oil. We need to sustain because Allah gave us a fortune. We need to use it. Of course, if we have converted to other product, but its market of the oil products like petrochemical or plastics is not as big as the market of fossil fuel, because most of the power generation worldwide is from fossil fuel. So you need to keep your fuel not just to save it in its reservoir by improving the efficiency, but you need to encourage other countries to use your fuel. I don't know how many of you are working in Aramco or SABIC. SABIC need the oil to manufacture it, to plastic and other things. Aramco want to produce more and sell to bring income to sustain other development. Even if you want to go for renewable energy, you need money, right? So when we talk about carbon sequestration, it's a part of the energy conversion process. And at the beginning of this lecture, I don't know who asked the question, he came late or what? I put here this, what is relation between carbon sequestration and sustainability? I started my lecture with this. Were you here when we started? Because your question was related to this slide actually. Did you come late? Who asked?
No, I was.
Can you please clarify your question more, because I didn't get the question. I think from my side that it is clear the relation between the lecture or the topic we are discussing, and power plants, because mainly we burn fuel there. And also this is my research. It is in this line with my master and PhD student. So the relation is very clear in my mind, but I want to understand more your question to see where you are from the picture I have. Can you please repeat the question or rephrase it?
Yeah, Doctor, since we got you clarified it, but from where my question raised,
Yes.
it's that we get this course part of mechanical, then we talk some carbon sequestration, which is technique. So that makes some questions from my side into the exam. So this part will be part also in the exam.
Yes, at least if you are worried about the exam, maybe I will give a short essay question or example, or a question like this one we discuss about this offset of CO2, or how much CO2 is absorbed by a tree or something. This type of example 1 and 2 might be a point, but this is not only the issue. We are talking about different ways how to make the combustion clean, right? Or the power plant environmental friendly. Why I want my power plant environmental friendly? To make the country leave my power plant in operation,
Yes,
right?
yes.
Yeah. So otherwise they will shut down my plant if I am exceeding the limits, or I will pay more taxes that will reduce my profits, right? But as a country, we are responsible now about our globe, aren't we? We are responsible about the problems that affect not only my country, affect other countries, right? We are affecting each other, as I said.
Yes, yes.
So
Yes,
these
yes.
type of questions are important. But again, I said at every beginning of each lecture, I will try to make a link between what we are discussing and what is the main objective of your master program. It is sustainability. Of course, even the program now is sustainability and renewable energy. I'm not sure if it is the official name now. We discussed it earlier to change the name to sustainable energy only. Now it is sustainable and renewable energy, both. Because introducing renewable is part of the contribution to sustain our source of energy, to make it continue for longer time for us to use it. That's why, first of all, to use it efficiently, and also using it efficiently help us to use it environmentally friendly. Yes.
دكتور مخيمر.
Yes, please.
احنا we have attended with you, and this is the third session and 1 office hour.
Yeah, of course, I'm willing. Actually, the first office hour, I think we delayed because you were preparing for your exam with Dr. Hunter, but I'm willing to give any office hour you want. I am free. I have more time now, alhamdulillah. So at any time, but the first one in the first week, you remember,
صح كان عندنا
you
اختبار.
delayed because of the exam, not because of me.
ما قصرت دكتور، بس كنت ابغى اسالك انا دكتور recordings, where will you upload it?
Actually, as you remember, the help session extended for about 3 hours.
Yes.
And it is too big. And the last part of it was general discussion here and there that is really not related to the help session itself, right?
Yes.
So I want to remove this part, as was pointed by some of you, that we need to focus on the help session itself. And then I'll give it to Dr. Hunter. Dr. Hunter, I think now he's uploading whatever records on giving you link in Blackboard on something. So if I clean it and see how focused it is, I will, inshallah, give it to Dr. Hunter, and Dr. Hunter will handle it or make it available to you.
And model 4 and 5 also we cannot find it on Blackboard.
I don't know about the recording of 4 and 5. Actually, I recorded because Dr. Hunter left the session. Usually the host is Dr. Hunter for our Zoom session. And he told me that he will record at the beginning. I think he was recording the other lectures.
Yes, it was recording. We can see it. It's recorded. All your sessions was recorded.
Yes. Yeah, only the help session I recorded. You helped me to record, right?
Yes.
So everything will be available to you then. Nothing will be lost.
Inshallah. يعطيك العافية دكتور مهندس.
And by the way, also we have the lecture itself put as PDF in your Blackboard. So you'll have both the record of the live lecture and also the document that you can print and write notes on it and so on.
Yes.
Actually, I upload the lecture before the lecture. I upload the PDF, and after the lecture, when we have some modification or add something, I go and update the version on the Blackboard. So you will have the most recent, the most full one. Even the first lecture that was long enough because it involved many basic things, I cleaned up. And you have two versions of the lecture.
I can see there is one full version and there is one short version.
That's 120 pages or slides, and the other one 33 slides or so. That the focus one. So the important, what I see even over the last 2 days, that you are really working on the homework draft, the first draft I put, and you are solving the problems, asking, and even discovering the typos we have. So this is good. You are going well. And I wish that this is for all the class, not only 1 or 2. So you took the time for the discussions. Do you want any break?
Yes, actually.
How long?
10 minutes break.
10 minutes. So now it is, let us say 1:38. If we start to 1:50, we'll be fine. 12 minutes.
Okay, دكتور يعطيك العافية.
1:50, I'll be back. Thank you.
Thank you.
Yes, Doctor.
Are you seeing my screen?
Yes, Doctor. Yes.
Actually, this is again a continuation of carbon capture. This will close the issue of, I think, conventional power plants, because we are going to start after, in the third session, sort of renewable energy part. Before I go to this, actually the questions you are raising, like what is a relation between what we are discussing and the sustainability or the main program, and also how the element inside each module are integrated to each other, are also important questions. Because you need to know, as a master student in that program, what are the main objectives, why these courses are there, how they are helping me. Actually, the global picture is that a graduate of this program should be a leader or decision maker or manager in the energy sector. That maybe after a few months or few years, you will make decisions, major decisions that affect your company or affect the country, right? Depend on what will be your position. But what we are preparing, we're preparing an engineer who will be a decision maker in the energy sector. So the other question you are asking, what is the nature of the questions that will come in the homework or in the exam? Because the last lecture, and maybe next lectures also are descriptives more than numbers. But we are trying to shed light at different topics. Of course, you need to, when we assess you, we give you clear and specific question, and you need to be trained to answer it. These all are questions. But looking at the overall picture and looking at the micro point related to the topic or related to the homework or to the quiz, all are not opposing each other. They can help and support each other. So please ask any question, but also you need to look how things are integrated. We are trying to make things clear to you, but also you need to open up and ask the questions you want. Okay?
Doctor?
Yes.
I have a simple question, يعني,
Please.
From my point of view. It's regarding the program, يعني, in general. Doctor, يعني, briefly, you agreed to teach, to be part of this program, يعني, and this is a good luck for us. يعني الحمد لله، هذا من حظنا الكبير إنه ندرس على يدك يا دكتور ونتعلم. أمانة ترى ممكن أنا أتكلم عن نفسي وما أدري إذا بعض الطلبة يتفق معي. الفكرة عن الماجستير يعني ما كانت مثل اللي الآن يعني يتم طرحها. يعني طبعا نتكلم عن هذا الماجستير بشكل خاص البروجرام، إنه طريقة حل الأسئلة وغيرها. أنا خريج البترول يا دكتور. طيب. وأنا عارف يعني إنه هذا الأمر نفسه كان في البكالوريوس، فما اختلف علينا حاجة. الماجستير الآن هو نفس البكالوريوس، اللهم أنه مواضيع جديدة.
ودي ميزة ولا عيب؟
والله يا دكتور ممكن أن تكون ميزة، وممكن ما أقول أنها تكون عيب، لا، ممكن تكون أنه يعني تطور إلى شكل آخر. يعني على سبيل المثال إحنا في أحد المواد الآن اللي إحنا ناخذها كانت مع الدكتور بسام طوابيني من الانفايرمنت. أيوة. الماتيريال اللي كان يعرضها الدكتور كانت يعني معلومات عامة جدا، وأمانة يعني ما من دون تقليل بالآخرين يا دكتور، ممكن كانت أكبر قدر معلومات إحنا استفدنا منه. المواد الأخرى إحنا استفدنا منها بشكل كبير، لكن مو بنفس القدر. ليه؟ لأنه المادة هذه كانت تركز على مفاهيم جديدة، وكانت تتكلم عن مصطلحات جديدة أو أمور جديدة علينا. طبعا في السستينابيلتي نتكلم. أيوة. فأنا ما أدري يا دكتور هل والله البرنامج كله يستمر على نفس يعني النظام هذا أو لا؟
زي ما أنت قلت إن البرنامج is covering energy in general and also interaction with the environment, like the Dr. Tawabini course and line. Even our course is in the same line. It's about energy and interaction with the environment. All are looking from different angle, but to the same target. And actually, since some of you are not a mechanical energy engineering graduate, so some topics in thermodynamics are important. And this is the nature of the course. We need to have these concepts clear. As the example I told you last class, that one of my students in thermal power plant and mechanical engineering, especially in gas turbine, is it why you are giving us details on the gas turbine performance, how it works, how I improve efficiency. It is for us a black box. Why you are talking about that? Then after a few years, he called me, he said, I understand why you gave us this and I want to come and give a session in your class. So if sometimes you don't, I don't know what is really concerning you about solving real thermodynamic problem like the undergraduate, and analyzing a cycle from thermodynamic view or a view not rather general. This is the old fashioned, but even to understand how you are going to use solar energy and geothermal, as we are going to talk now. If you don't know about Rankine cycle, if you don't know about Brighton cycle, I don't know how you make the link, or how you, as I said, you'll be decision maker, how you will select the right choice. There are basic things, you should be aware of it. And this is Dr. Hunter and myself are trying to build or to give you the roots. Like when you build any building, it needs foundation, isn't it? So our course has some foundation that some of you might have it if he has taken in the undergraduate any course on thermodynamics, but we are revising this, and if you don't have it, we are trying to give it so that we can, you can go the way you want later. If you have a strong root, you can grow bigger, right? So we're covering the basic things. It's not a general information course. It's a basic course about energy conversion, efficiency, and different types of energy. That's why you will have different topics like steam cycle, gas turbine cycles. When we come to the combustion, it should also cover basics of combustion. We didn't take you to the real combustion, but we give you a quick idea how to make it environmental friendly, but we didn't give you the combustion details. It's science by itself. We have two graduate courses. We have one chapter in thermodynamics too, but we have two courses at the graduate level in combustion and emission. We didn't take you there. And the second thing, we are going to now to nuclear energy as one of the ways to produce electricity at the end. And I will go for solar energy. Dr. Antar will give the PV, I'll give the concentrated solar power. All are different, I'll give the wind energy also, are different ways to convert different source of energy into electricity or into mechanical energy. So the topics you might see it is scattered: wind, solar, nuclear, conventional, but they are all related. I mean, when you look at the Ministry of Energy, isn't all these types of energy under it?
صحيح.
Right? Well, yeah.
صحيح.
So this is the nature of the course. It's called Advanced Energy Conversion. We are trying to touch part on the environment, but we are introducing little part. Also, Dr. Antar gives some on the economics, but you have another course for economics, you have another course for environment, but at the end, all courses are integrated with each other. So we cannot have the same, all courses similar. Each course will cover something in depth and something in general. But when you put all these courses at the end of your degree, then you will see the picture. They are really integrated because it took time from the electric department to form this program. I was in the graduate council, and after 2 rounds, they came and they updated. They tried to give the new version you have now. And this all based on discussion with the faculty, discussion with the stakeholder, I mean the companies, discussion with the graduate who graduated from last sessions or last years. All this input, not only from faculty, it is from the companies, from the students who graduated, from the students who are studying. They made a lot of surveys. If you have another session to talk about how the program is being developed, how being updated, it is based on inputs like yours now. So any other question?
Doctor, I just want to ask about this carbon reduction concept.
Yeah. Yes.
I heard about new technology coming, oil-free compressors. Can you elaborate what this?
Let me finish, and then toward the end we'll have other discussion. If we didn't answer your question, then you can raise it again, please.
Okay, thank you.
Right. We have another type of sequestration. Is a geological storage of CO2. Sequestration, as you know, it is just separate CO2 from whatever other product, like in combustion, we said, combustion mainly we burn with air. So we have nitrogen as main product, and then CO2 and H2O. How to separate CO2 and then store it. This is called carbon capture, just to catch the CO2 and then store it or sequestrate it. Now, the first step in geological storage is, as it's called, geological storage in the literature, as an option that need what? First, we need to remove the CO2 from the stream of combustion byproducts and accumulate it in some stable location other than the atmosphere. In geological storage, there is no human controlled conversion of CO2 to other carbon-containing material. But we just keep it as it is. We sequestrate it in what we call, we might suffer from leak. If you store in the ground, as we will see, after some time, it might leak back. And this is, of course, risk that if you accumulated huge amount of CO2 in a reservoir, old oil reservoir or old salt reservoir or coal reservoir that now empty, you can add CO2 to it. But if there is any reason that this will leak to the surface again, it will be a very big risk. So as any CO2 sequestration, we start with the separating CO2 from the combustion gases, which represent 10 to 15% of volume of the combustion exhaust. And then we need like how to separate this, how to separate CO2. As I said, if we have a combustion product that is nitrogen majority plus carbon dioxide plus H2O. To remove the H2O, we can cool the gases, then H2O will condensate. But how the nitrogen? Nitrogen is very well mixed with CO2. So we have either ways to absorb material that absorb CO2 in it, some chemicals that absorb CO2 and leave nitrogen free, so we take rid of it. Then this material that absorb CO2 relatively at low temperature, then after that we can heat this material, then CO2 will go out as gas again, and we take the material or this chemical that is free of CO2, we reuse it. And the CO2, we take it, suck it from the this separator tank, and we take CO2 with a compressor, help of compressor, sequestrated in the ground, it's under pressure, of course. There are now new emerging technologies that we separate nitrogen from the beginning by separating oxygen from nitrogen from the air by oxygen separation technology, either cryogenic or using oxygen transport membranes. We separate the oxygen from nitrogen. Of course, nitrogen we can exhaust to the atmosphere and take oxygen and burn the fuel with pure oxygen. Maybe we add CO2 to it, a sort of CO2 circulation. But the product will be what if we are burning, the oxidizer now is a mixture of oxygen plus CO2. Then we burn the hydrocarbon, we produce what? CO2 plus H2O. H2O, I can cool the exhaust gases, condense the water, I have it liquid, and then I have CO2, compress it and sequestrate it. These are emerging technologies, but it has cost, of course, to separate oxygen from the air. But the normal process that add no, I mean, when you have this oxy combustion, you need to modify your combustion system. You need to add the plant of air separation. And the other way is to leave your plant as it is. Then you have exhaust gas treatment way. As I said, by chemical looping, you have some chemicals that absorb CO2 and leave nitrogen alone, get rid of it. And then you have the liquid, the solution that have CO2 dissolved in it, you heat it again, then you leave it to heat it again to take the CO2 out as a gas. Of course, there is no chemical reaction with the liquid or the chemical material. So you just physical dissolving in the low temperature and separation at high temperature. So here you have some energy you pay in circulating the liquid between the two containers, and also in heating the dissolved or the solution of chemical and CO2. You need to heat this sort of energy. And also when you put this system on the exhaust of the gas turbine or the combustion chamber, you are adding a pressure resistance or a pressure drop friction that will reduce the power output from your plant. So there is penalty always when you add carbon capture technique, either in the beginning in the pre-combustion by oxygen separation. This is energy demanding process, or when you separate it also, this is energy demanding process. But at the end, you see the cost that you will pay as a penalty for emitting CO2 to the atmosphere, or the cost of separating CO2 and modification you need to add to your plant. You compare the two costs by the economics, as you learned with Dr. Hunter, and last class we discussed this, and we'll continue in the help session solving problems on that cost analysis, and see if you have which technology will go for to give you a safe profit. Then again, let me show you one of this example. I gave it last session. Let us look at it more closely. This is a chemical looping process for natural gas combustion with the carbon capture technique. Now this is the gas turbine. Even it looks small here, but this is the nature of gas turbine. It's small in size compared to the power produced in comparison with the steam cycle. This is a combined cycle. You have the gas turbine here. You suck the air from the atmosphere from the this is by this compressor, and also the fuel come from the tank by this pump or so. Come to the combustion chamber, burn it, and rotate the turbine. Then after the turbine, you have the exhaust, and coming to the heat recovery steam generation generator, when you have different coils where water liquid is circulated, converted into vapor, then superheated. Then you take this steam to rotate the steam turbine. This is fine. What about the red line where it is the gas line? The gas product, after heating the water, producing the steam, the exhaust gas, we take it to what we call chemical looping process, where we have the absorber and generator. What are these yellow tanks? This absorber is a tank full of the chemical material we have, where we introduce the exhaust gases at relatively low temperature, because we are trying to cool the gases all the way from the gas turbine up to the exhaust point here, so it can be dissolved in the absorber, and then it absorbs the CO2, but it leaves the nitrogen free, so we can leave the nitrogen, or mainly nitrogen and very minor CO2, we leave it to the chimney here. But then after that, this chemical that have saturated with CO2, we pump it to the other tank, which we call the generator. When we heat it, and then CO2 will be separated as bubbles, as a gas at the top. We take the CO2, we cool it somehow, and then compress it. Why we cool the CO2? Because we are heating the chemical to release the CO2. But if we compress the CO2 while it is hot, we are going to consume a lot of power in the compressor. And we talked about this in the concept of cooling the inlet of the compressor, reduce the power consumed because you are reducing the specific volume. One of you will see the link between what is we are saying as a thermodynamic concept, that the work in the compressor or the shaft power and compressor and pump integration VDP, and we need to reduce for whatever delta B we want. This is what we want, but what we need to control to reduce the power is to reduce the V, the specific volume, and we do it for gases by cooling. Now you can see the link. Otherwise, I will say cool, then you will say, why we need cooling? Just that the cooling cost $100,000, remove the cooler. Is that correct? So this background that you are taking as point here and there You need to really understand it. You need to pay attention to it, and you need to use it when you make any decision. So that's why we cool the CO2 after the generator or separator. So we compress it and we take it to what this actually may be not one compressor, it might be more than one compressor with intercooling to reduce the power consumed, to raise it to very high pressure, and then inject it into the reservoir that is underground. This, as I said, yes.
We are capturing the CO2 that's coming from the boiler.
Exhaust. No, here, yeah, from boiler or from the heat recovery steam generator, the same concept. Yeah, you take the exhaust before it go to the chimney, you absorb CO2 separated by the chemical absorber, then release it because now you don't have nitrogen. When you this chemical is selective for, you have the air coming, exhaust gas coming, nitrogen and CO2, and H2O. Of course, H2O will dissolve and nitrogen will not react or dissolve. It will be like going as bubbles at the top. You take it out and the CO2 will dissolve in this liquid chemical. Then you take this liquid by the pump, give it to another tank that is being heated by any means, by hot gases, by whatever, here to make this process efficient. There are different details on here, but the concept is you absorb CO2 at low temperatures, then separate it at high temperature. Because most of the gases that dissolve in liquids at low temperature, it doesn't dissolve in it, it separates itself at high temperature.
So we dissolve the CO2 in water?
Not water, actually, it's sort of chemical. Whatever the chemical, it's a liquid, yes.
And then it goes out as steam?
It goes out as a vapor, as a gas, not a steam. Steam is water vapor. Steam word, as a word, is linked only to water.
Okay, then this liquid, that the CO2 was dissolved in it, we take it out?
No, we keep recirculating, we keep using. I mean, there is a loop here. If you see that you give the pump and then return it back. Actually, this pump, this or pump or heat exchanger, whatever the arrangement here, you take the liquid from the absorber to the separator. After you separate CO2 at the top, you take the pure liquid back to the absorber. So it's recycled. You can see here for the between the two tanks, there is a loop, circulating loop of the liquid. It come at the top with the CO2 dissolved in it, might be like a shower here. And then when you spray it down, you give a chance for the CO2 to liberate itself. So CO2 is light compared to liquid. Liquid come down without CO2, and CO2 as a gas, it go at the top. You separate it, physically separation. Mr. Dia?
Yes, doctor.
You raise your hand?
Yes, doctor. I didn't understand here the waste steam, the expression of waste steam. So what I know from previous classes that here we are dealing with a closed system. So we don't have a steam that will go out of the combustion or will go out.
Where is that?
Sorry?
Where is that you're talking about? At which component?
I'm talking about the waste steam as expression, okay? Here, the title, removing CO2 from waste steam, okay? What I know that we have a closed system, okay? So from where we're going to get waste steam?
Oh, maybe the title is not complete. I mean, the exhaust really, it's not a steam. Let me correct this. Maybe due to the size or the font is not complete title. This is
me, Dr. Ismail.
Yes.
Actually, it's a waste stream. Stream.
Yeah.
It's a stream.
Yeah. It's not, I mean, steam. We don't have, yeah. Because we do have some steam that's why I asked about the component, which you might have leaked to fitting or so. But here, this is the exhaust. The waste means the exhaust. I will correct it. I'll write it from the exhaust just to avoid any.
Dr. Mkhamer?
Yes.
معليش سوري أنا اللي سألت عن
Yeah, you are welcome, no problem.
ال
Don't say sorry to ask. Sorry not to ask.
Okay. I'm just still wondering if we'll release the CO2 again. Why are we taking it?
No, we are not releasing it. I ended up here. I said we go it for sequestration in a reservoir. That's why we have a compressor here.
Okay, sorry.
I didn't say we release it. Just the cycle, actually, the drawing doesn't allow us to draw more, right? But
So
at this point, actually, the pressure is high. Maybe the next picture slide show it better. Actually here, this is the chemical looping. Here the flow gases going to the chimney, but actually you put the chemical absorber in it in its way. So you take the nitrogen at the top separated, you give it to the chimney, but the liquid that is having CO2, you take it to the separator, and this separator will separate CO2, and you take the liquid back to the absorber. So this is the loop of the absorber. This is called the absorber chamber. This is the regeneration chamber. Regeneration because we are going to, as we are cleaning the liquid from CO2, and we take it back to absorb new CO2. But the gases here that go to the chimney should be CO2 free. But it depends on the quality of the chemical you have. You absorb all the CO2 or you absorb a part of it to just be within the limits you have. Yes.
That's a new thing in the plant, or it's available long time ago?
The chemical looping is known long time ago, but nowadays you need to install it. I mean, you need to add it to your plant. If you don't have it, so you will add it, right? Like oxygen separation, the new technology or the other technology we have it. This oxygen separation is known long time ago because in all hospitals you have oxygen bottles, right?
Yes.
From where they got it?
Okay.
From the air. You have a factory, like many factories around us in the eastern province. They compress the air to very high pressure. They cool it to very low temperature, so it become liquid that is mixture of oxygen and nitrogen as liquid. Now you heat them again slowly, so the nitrogen will boil at different temperature from the oxygen. You separate them, and you take the oxygen in bottle. Maybe you release the nitrogen again, or you take it for another industry, like fertilizer industry or something. But we have this technology of oxygen separation from air is known long time ago. But now they introduce this into power plant for pre-combustion to separate CO2. How is this? When I burn any fuel, which is CXHY, I burn it with air. Air have oxygen and nitrogen, isn't it? When we have this combustion, CXHY plus oxygen plus nitrogen will have CO2 plus H2O plus nitrogen again, because nitrogen is inert. It doesn't react unless we have NOx. So mainly, you can separate H2O from the product by cooling, as we did, and separate nitrogen. How to separate oxygen from nitrogen? We use the chemical looping, but it has its advantage and disadvantage. But the other way is to separate nitrogen from the beginning, and this will help even to avoid the formation of NOx or nitrogen oxides at high temperature of the combustion. And now you separate it by oxygen separation. Oxygen separation using the technology of cryogenic or cooling, compression and the cooling to very low temperature and very high pressure, as I said, is well-known technology. But it is energy intensive because you need a lot of power to compress the air to very low, very high pressure, and to cool it. Cooling is also energy demanding. So they introduce nowadays some material called like membrane. When you pass the air around over it, it absorbs the oxygen and leaves the nitrogen. But you need to do this at relatively high pressure and high temperature. So also it is energy demanding, but not as the cryogenic technology. But the material also development for the ion transport membrane is under development, and they need to produce a large membrane for mass production. It is underway. Some company like Air Product, they tried both, but still they prefer the cryogenic, but they are putting some research, even with some colleagues in our department, for development of ion transport membrane. So whatever the technology here to separate the oxygen, you take it and burn it in the gas turbine. The top one is the gas turbine. And then the gas turbine, of course, operate this electric generator. Yes. And then you take the exhaust gas to Rankine cycle, like the bottoming cycle. And the exhaust CO2 now, it is cooled because you are heating the water and cooling the exhaust gas, that mainly CO2 plus H2O. In each stage, you have some water condensate you collected, but the red line mainly CO2, and you have always condensate of liquid water. So you raise the pressure of the CO2 into different stages of the compressors. Then you, whatever water condensate, you take it, and at the end, that product that is mainly CO2, you sequestrate it. You see, you take it to a reservoir, actually, after raising its pressure. So you are not just releasing to the atmosphere, but here the capture, you separated nitrogen from the beginning. So you have the exhaust here coming from the turbine is mainly CO2 plus some H2O or water. You cool and compress, cool and compress until you reach almost to pure CO2, almost pure CO2. Here 90.4% is CO2, right?
Yes.
Yes. So this is also another way to separate CO2 from the exhaust. There are other ways now that for direct sequestration, if you have an industrial area and you have CO2 coming from many chimneys and you have a windy place, so you can design a sort of a duct in which this wind or stream of CO2 plus nitrogen go into the duct without really needing a compressor for suction, or so then make the separation by chemical looping, or so then you need to raise the pressure of the collected CO2 and inject it into the ground, into the reservoir. What I want to say, why not to take the exhaust directly, all the exhaust? As I said, if I have 100 meter cube of exhaust gases, it mainly maybe 90% of it or 85% will be nitrogen and the remaining is CO2. So when you compress all this, you need to pay energy and money to compress all the exhaust, including the nitrogen that you don't need to store it, right? So first, the cheaper is to get rid of the nitrogen, and then you have almost to pure CO2. Now it is forced to pay energy to raise its pressure. Why we raise its pressure? To be able to compress it down, under the ground. Now, some companies or some ideas is to use this, since we try to store CO2 under the ground, why not to use it for enhanced oil recovery? As I told you, maybe in the discussion of the help session, we have enhanced oil recovery. What does mean enhanced oil recovery? That in many places on the world, the reservoir that have the oil or natural gas is not at a very high pressure. When you dig the well, the gas or the natural gas doesn't come up to the surface by its own pressure. But in our area in Saudi Arabia here, the oil is at very high pressure. It comes by its natural pressure, come to the top. But after some time, after you take from this oil well, more oil and more natural gas, the pressure down in the reservoir reduced because the content has been removed up. So they flood with water. They get pipelines from here in the Gulf to where the reservoir is. They pump the water down, so they raise the oil level and gas, and they keep the pressure of the reservoir. In the first stage, they call the first, which is naturally production, they call it the first stage. It produces up to from 10 to 20% of the oil content. And then with the water flooding, it might produce the up to 30%, but still you have from 60 to 70% heavy oil that is not able to come out. So now they are saying, since we have exhaust gas, why not to inject CO2 into the ground? It will do two activity. I mean, I am sequestrating and I am pushing or raising the pressure of the reservoir to produce more oil or more natural gas. Of course, when you have the natural gas come out, it will have some CO2 in it. And you need to separate the CO2 and pump it down back. So this is something of even in coal reservoir where you have coal, you can actually inject CO2 and some steam. Then you will produce methane and waters. Then you can separate the water and take the methane. If you have some CO2, you need to separate this. These are ideas how to make the sequestration, and at the same time, you produce more fossil fuel. This is some places in US that they use this technology of enhanced coal biomass reservoirs. You need to just get an idea how much you can sequestrate CO2. You can here in this reservoir in San Juan sequestrate up to 1.4 gigaton. So it's huge, but also it has a cost. One of the examples that you have, suppose that you have CO2 output from the plant in example 6.9 in chapter 6, is piped to coal field in Indonesia. It's the figure I showed in the figure, where it is 100% injected into the field for sequestration and generate methane. Assume that the natural gas production without CO2 injection has been exhausted prior to the project, and the methane is worth 10.5 gigajoule. For how long will the coal field be able to sequestrate CO2? What is the annual value of the methane production? So solution here is that from example 6.9, the annual coal consumption was 2.6 million ton per year with a carbon content of 85%. The resulting CO2 is this from burning the CO2 or burning the 2.26 ton or million ton of CO2. This produces CO2. Now, since the total capacity of the field is 370 million ton of CO2, there are 52 years. How I divided this number, 6.404 million ton production, and this is the total capacity. I divided 370 by 7, and then it gives these 52 years that I can sequestrate. The conversion rate of field is like here from this table. You can, this in Indonesia, this is the sequestration, this is the recovery, and this is the ratio 267. We use it to find out how much methane we'll get. So this is the energy we produce from the methane, and at this price, 10.5, the value of the gas output is about 720 million per year. Now, if you use this CO2 to inject it in a coal mine or something, then you will produce 720 million worth of gas or methane per year. But of course, you will pay cost. To transport this CO2 from the power plant to the coal mine and injecting it, you need compressors. So you need to see what is the net profit you have. Again, injection in saline reservoir, like you inject in these coal mines, you can reject in a saline reservoir. Why in saline reservoir? because saline water, it's underground water that is not useful for irrigation unless you have a desalination power plant that also will cost you. But let us say in US, there are many saline reservoirs, they inject CO2 in it, and CO2 react or with the saline water. And I think in some company in Norway, yes, they have injection or they have a power plant that produce 1.1 million ton of CO2 per year, and they remove it somehow, they sequestrate it under this saline reservoir. But as you can see here, this is the power plant and the pipeline where they inject the CO2 under in this aquifer. Also, it reacts with some chemicals inside, like this calcium carbonate or magnesium. Then this is the, you will have the CO2 like bubbles, hydrodynamically trapped gas inside. But again, this is the sort of analysis. If you have in the aquifer some porosity phi, and the volume of the aquifer is V, and the water in the actual, how much is saturated from previously injected CO2. So this is the volume of the CO2 you can inject in that reservoir. Of course, since CO2 is an ideal gas, we can say number of moles equal BV over RT, and then we can substitute here to from this how many molecules we can substitute here by BV over RT. So just a quick here example that the sequestration in literature suggests $0.01 per kilowatt hour may be feasible. This example is saying for the supercritical plant in example 6.8, supercritical power plant is the efficient power plant, but also you have combustion in it. You produce CO2 from 15 of such a plant in example 6.8 is piped to a saline aquifer where it is injected. The aquifer is approximately 1,000 kilometer long and 5 kilometer wide, and average depths of 1,000 meter. These numbers, length, width, and depths give you the volume. You multiply these three numbers, 1 million meter and 0.5 million meter, the width, and 1,000 meter. You multiply all together, give you the volume of the reservoir, which is here V sub R in this equation, right? Here. You need all the aquifer volume is available, so there is no saturation, or the water you didn't inject any CO2 before. This SW is 0, right? So here, and it says the pressure in the aquifer is 500 kilopascal on average, and the temperature is 325. If the plant function for 75 years, this power plant is working for 75 years, is there sufficient capacity in the aquifer to sequestrate all the CO2? Of course, to answer this question, we need to know what is the rate of CO2 production from this example 6.8. So we have to refer back to it and get from there how much CO2 is emitted, or how much megawatt hour is produced per year, and then we translate it to CO2 emission, because we have relation from how much CO2 is produced per megawatt hour. So after that, we use this number of production of CO2 per year, and we substitute in the equation and get the number of years, using the volume of the tank. Then he's saying if the total cost per ton CO2 sequestrated, including the repayment of capital cost and all cost, is $25 per ton, by what percent does the cost of electricity increase due to sequestration? Because as I said, sequestration needs transportation, you need decompression, these all are additional cost. So the solution here, we got the volume of the reservoir, which is 510 to the power 14 meter cube, and this is the pressure over RT, the temperature, and time 0.1, the porosity of the reservoir. So you have 9.25 times 10 to the power 15 mole. But at 44 gram per gram mole of CO2, this convert to this number of tons. And then from the example 6.8, as I said, we should refer to it, it consumes 1.47 million ton per year of CO2. It generates this much. So the amount of CO2 generated by 15 plant over 75 years, we multiply this number by 15. Then therefore it is times 75 as well. Then there is adequate capacity because you see how much is the volume of the reservoir. And this is the additional cost. If you have how many ton, you multiply this by $25, it gives you the cost $36 million per year for sequestration. Then spreading this cost among 3.07 billion kilowatt hours generated, then you add this to the, he made simple analysis. He has the cost, the levelized energy cost in dollar per kilowatt hour. Then he saw how much energy, money he need to pay for sequestration divided by all energy produced in kilowatt hour, then add this incremental cost, and he found that 34% of the cost will be due to sequestration. Again, other geological options is to take this CO2 and pump it underwater. But of course, in this case, in the ocean, you select some places that is far from the living areas, and you need to put CO2. Of course, you convert it by high pressure into liquid, then you pump it down deeply 1,000 or 2,000 meters. Then you have the CO2, you know, its atomic mass is 44 kilogram per kilomole, and water is 18. CO2 is heavier than water, so it will stay down as a lake under the ocean water. Then we can sequestrate up to 30,000 to 40,000 gigaton of carbon. But this is, again, it has its own risk and also direct or indirect impact on the marine life in the ocean. So we have this risk always with carbon capture and sequestration underground or under the ocean water, like risk of leakage. If this CO2 leak back to the surface, it might be in huge amount, and then we are actually making adverse effect on our globe. Also seismic activity, when you store mass in a reservoir that is empty, then you might create some risk of earthquakes or something. Then if you have earthquakes, you might have some cracks. Then these cracks might lead to leaking of the CO2 you stored. But also there is important issue. I think our friends in Earth Science and the Petroleum Department are studying, because when you put or inject CO2, as we said, even for oil recovery or just for sequestration, this CO2 might react with the material or in the rock shell that cover the cap or the cap shell that of the reservoir. It has a cover from, I think, sandstone material, or I don't know the detail, but it can react. They study, our colleagues are studying how this CO2 will react and how it will affect its strength or ability to sustain earthquakes or something like this. Actually, the other important way for sequestration is to convert CO2 to inert material. I mean that it can react with material like carbon or magnesium and produce carbonate, calcium carbonate or magnesium carbonate. And then this means it is like a rock. Then it you made the CO2 not a gas that can leak to the atmosphere or outer atmosphere of the Earth, make global warming effect, but it will stay on the Earth as in the form of rocks. This is one way, but a more smart way is to convert CO2 to a product. Instead of looking at CO2 as a threat, we look at it as a raw material. I think SABIC is looking at that. This is not, this is how to sequestrate or take the air from the CO2 from the atmosphere, sequestrate it, inject it, and if you have the power plant, this is the energy conversion, you have the atmospheric CO2, you can recycle or you sequestrate it. This is not the, before I leave this, is to convert CO2 into product. SABIC is having some project to convert CO2 into plastics. There are some technology under development, SABIC trying to push this. Also, you might convert CO2 into fuel by making a similar process to photosynthesis. I think we have Dr. Gondal in physics department is trying to do something like this to convert CO2 into fuel. So I will stop here. Again, this lecture and sort of descriptive lecture, but it has some numbers, simple numbers, just to have rough estimation of the cost due to sequestration, how much if you use indirect by tree, or how much if used by chemical looping or using by sequestration in aquifer. This type of questions, I might integrate in a question that to compare this to that, how much is this cost, how much is this cost? This, if you're looking how I will put the question related to this topic. But more important, how these topics might be introducing a solution for environmental impact of fossil fuel and use it as a source of power that we need electricity in our daily life. How, when we get it from fossil fuel, we have the environmental impact, how to reduce this impact, by what techniques, how this will affect the electricity cost, how it will affect our environment, how it will affect the performance of the plant. You have any question? We have, again, now the time is 2:44, so we have less than 1 hour. So you have any question, then we'll take a little break, then we'll start the last session. Hello?
Thank you, Doctor. Thank you.
Yes, Doctor. No problem.
Thank you, Doctor. Thank you.
You have no questions? So the last session will be about geothermal application. It's sort of renewable. So we can start after how long? Now 2:45. We didn't take an hour. It is less. Can we take 10 minutes also? Break?
As you wish, Doctor. After 10 minutes, shall we start or at what time?
Yeah, because we need to finish as soon as possible. To leave you have some of the weekend.
10 minutes is good.
Okay, let us break for 10 minutes.
Doctor, I have one thing, please.
Please.
It's just suggestion from my side, okay? I prefer to see the lecture more on, if we have integration with these words and this calculation with videos, with more pictures, so it will be more enjoyable for us and more understandable for the material that we're going to take.
Dr. Hunter and myself find some animation of videos about the gas cycles. I will share the link with you. Is this type of videos you want?
Even for today lecture, I believe if we're going to search for these things on the internet.
You will get it from the internet. But if it is available in the internet, what is the meaning of that? I bring it and run it for you, but I can get the links and give it to you, then you enjoy it. In addition to the lecture, because I'm trying to focus on concepts and also explain quickly how the calculation, because these material all in your book. So you can read it anytime. But of course, having animation make the picture is clear. But I don't think the lecture time that is 1 hour is a room where we run videos that is available in the internet.
Yeah,
unless I have something, unless I have something really valuable, I'll share it with you here. Otherwise, I'll share the links with you.
ويعني دكتور I'm not looking for something يعني very long. Yeah, sometimes 2-minute video it will be more clear and it will deliver the idea okay more faster يعني than maybe 100 slides.
I try to get this you know, this cartoon or drawings to give you a quick idea, but again to have videos whatever 1 or 2 minutes or 5 minutes, I'll share the links with you.
Sure, doctor. Thank you very much.
Okay, you're welcome. Assalamu alaikum. Are we back?
Yes.
So all of you are here. Any question before we start? Of course, you will have some questions, but I need you to read the lectures. See, the book is very nice and very interestingly written, so you can read more because I talk some key points plus the important examples in the chapter 7. You can read all, and also we'll try to have help sessions soon to continue the economic part and CO2 taxes and this sequestration cost. So if you are willing to have 2 help sessions, I'm ready. Just decide about the time and coordinate with Dr. Hunter, with me, to see what are the suitable time. I think your regular one is a Tuesday at 8 p.m. I'm ready for that. If you have any question, you can send me the list of questions so I can prepare examples or something about it. I'll start now the geothermal applications. Geothermal application is one of the renewable energy, but since we are talking about renewable energy, let me tell you that Department of Energy in US, like a Ministry of Energy here, they consider renewable energy, energy efficiency. If you raise the efficiency of your production plant for energy or your consumption at home, appliances like refrigerator, air conditioning, they consider this one source of renewable energy. So energy efficiency or raising the efficiency of your appliances is not just for fun or saving your money at home, but it saves more in the production side. So that's why I think you have a course on energy demand side. If I am not mistaken, now one of the most important application, as I said, in renewable energy, it's help sustain our resources. As I said, efficiency, yes, it's one important source to reduce the consumption of our energy sources. Either it is conventional like fossil fuel or even renewable like wind energy, solar energy. What is the geothermal energy? Actually, there are 2 applications of geothermal, what we call shallow geothermal application, that we need the near surface of the ground to use it as heat source in winter or heat sink in summer. This sort of application is very coming or growing worldwide. Even Saudi Arabia is trying to explore the use of shallow geothermal, not to use it as a source of heat, but to use it as a heat source or heat pump for air conditioning systems. This would raise the efficiency actually of your air conditioning system. Why I am talking about energy efficiency of air conditioning systems? Because on the demand side, 70% of the electricity produced and used in houses or in building go to air conditioning. And in general, Saudi Arabia is consuming 55% or more, maybe 55 to 60% of all energy produced, electric energy produced in Saudi Arabia is used in air conditioning. So if you save 1%, 2%, 5% of the energy consumed in the air conditioning in Saudi Arabia, you are saving a lot of million of oil barrels, a lot of even building new plants. Yes.
Doctor, I always see heat pumps. What's the meaning of heat pumps?
What is the meaning of water pump?
Oh, okay, I understand. Okay.
It's pumping water from low level to high level, right?
Yes.
So heat pump is pumping heat from low temperature to high temperature. So we use it in summer to take heat from our houses at 20 to 22 degree or 25 degree and pump it to the atmosphere outside at 45, right? That's we call, it is cooling, but it is heat pump. In winter, we can do the opposite. We can take outside the heat from outside that is at 10 or 5 or 12 degree and pump it to our house at 25 degree. So always the heat pump used to take heat from low temperature and dump it at high temperature. Usually when we call it heat pump, the common name is the heating purpose that is commonly used in North America and Europe. And air conditioning is commonly linked to cooling in summer. But actually the device is one that work on the same principle. You have a compressor, evaporator, condenser, and expansion valve, and you take from the heat from low temperature space to dump it to high temperature space. Either you make benefit of the heat, dump it, or the heat extracted. I mean, you make use of cooling or you make use of heating, but the device is one. It's the refrigeration cycle or air conditioning cycle. Let me give you the other angle of geothermal application that very deep in the ground. Yes, 1 minute. Very deep in the ground, we have, the ground is hot. We have rock hot. We have, even if you go down, you might find magma and lava that is at high temperature. So can we use this to generate power? The answer, yes. Please go ahead, ask your question.
دكتور كنت ابغى اسالك لسه ما وصلت لي كيف الجيوثيرمال ابلكيشن حتستخدم في raising efficiency للاير conditioning systems.
Let me tell you soon. You are Naif. Naif or we have Naif Al-Hanazi and Naif مش عارف الاسم اقراها.
الجغدمي جيم غين دال ميم ياء جقدامي.
جدامي ها؟
الانجليش جقدامي، العربي جغدمي.
جغدمي. ونعم.
نعم.
ونعم.
الله ينعم بحالك طول عمرك.
طيب let me of course you're having your attention here on how to use the geothermal for power generation or raising the efficiency. This is very good question. Always try to remember coefficient of performance of Carnot for heating is or cooling is T high minus T low or T low over T high minus T low. So T high minus T low by the coefficient of performance. Anyway, it is efficiency is 1 minus T low over Ti. Whenever you have T low is low, really low, you raise the efficiency. This is a quick analogy. So when you actually, in the air conditioning, do you know what is the air conditioning cycle or refrigeration cycle, how it works? Do you know this? Compressor, condenser, throttling valve, and the evaporator. Do you remember the heat, the window air conditioner? Hello?
Yes.
The window air conditioner, what does it have? It has two coils, like the car of the radiator of your car, one outside the window, one inside the house, right? And the compressor is there circulating the refrigerant in between. So when the compressor rotates, it creates suction at the inlet, low pressure, then we'll have the refrigerant at low pressure, low temperature. pumped by the compressor at high pressure into the condenser, then you will have the refrigerant at high temperature, high pressure, high temperature. Then you throttle it back to low pressure, low temperature, and cycle continue. This is the simply the window AC, right? The window air conditioner or refrigeration cycle. It is these main 4 components, regardless of whatever accessories, controls, fans or not fans. This is the 4 component. Evaporator, that we have low pressure, low temperature refrigerant. Compressor, raise that vapor pressure, temperature to high pressure, high temperature in the condenser. So the throttling valve to low pressure to, from high pressure to low pressure again, and the cycle continues. Actually, when we put this evaporator or coil that have refrigerant at low temperature, it can suck heat from whatever source at low temperature, then dump this heat from the condenser to a place that have high temperature. This happen actually in our window type, that we circulate air of the room on the evaporator coil and inside our room, so we feel cold. The air get colder and circulated to us by the fan. And the condenser is outside the house where it has hot refrigerant gas, so the fan circulates the outside air that cool it. Of course, the air in the outside air temperature 45 or so, but the refrigerant maybe inside is at 50 or 65 degree. So heat transfer this vapor, and the condenser will condensate and cool down to condensate like liquid. Then we have the throttling valve to throttle to low pressure and continue the cycle. And as it is clear, so this, with the help of this compressor, we are absorbing the heat from the surrounding here at low temperature in the evaporator, and then dumping the heat into with the help of the compressor to the condenser to make the refrigerant at high temperature than the outside hot environment. So we give the heat, dump the heat out. So this is the main principle of heat pump. Take the heat from low temperature environment and pump it to high temperature environment.
So
here,
we are using fuel right here. It's not geothermal.
What?
How we are taking it from the earth at low pressure, low temperature, right?
Right. This is the shallow geothermal. Yes.
Yes. Then how we are making it hot? Using
by the compressor.
The compressor, from where it gets the power? Or
it's electricity.
From fuel, right?
Yeah, from fuel, of course.
Okay.
But the point here, let me explain. This arrangement here are for heating a house. Heating a house in winter. Right? So in summer, we'll have our condenser will reverse this cycle, and our condenser, this loop will be the condenser. I mean, this coil will work as a condenser. How to reverse this cycle from cooling to heating, it's an important issue. I can explain it sometime later, but if you see in the market, you will find the air conditioners, different types, 3 types. One cooling only, one cooling and heating electric, one cooling and heating reverse, right or wrong?
Yes.
If you see Saco and cooling only, so it has this cycle, and you put this evaporator in your window inside the house, or this is the cassette of the split system. It will be inside the house. And the condensers that is red or brown here will put outside. This is for cooling only. For cooling and heating electric, and when you press the heat in the electric system, you have electric heater here, and the compressor will not run. Just electric heaters that, like this electric heater that is 100 riyal, you put it in the ground, and this electric heater will turn on, and you have the fan circulate the air on this heater, but no refrigerant is circulating. Compressor is not working. Okay? What about the cooling and heating reverse? Cooling and heating reverse, it is the same cycle, but what happened, you have here in a valve, they call 4-ways valve, that to connect, actually the evaporator, when you connect this coil, as I said, in the window type, you have two similar coils, like the car radiator, right? One inside, one outside. The coil, if you connect it to the inlet of the compressor, it will work as evaporator. Why? Because the suction will create low pressure in that coil. So low pressure means low temperature. So it will work like evaporator, right? Okay. But if you connect it to the outlet of the compressor, then it will work as a condenser because it will be the one at high pressure, high temperature. So the evaporator sucks the heat from the surrounding and the condenser gives the heat to the surrounding. Right?
Yes.
Clear enough? So in summer, I will put this evaporator, or I'll keep the evaporator here connected to the inlet of the compressor, and my house is being cooled, and the condenser will be the coil outside, and it will dump heat to the outside air, right?
Yes.
Okay. Now, if I reverse the connection, so instead of connecting here, this evaporator directly to the inlet of the compressor and its outlet is directly connected to the condenser, what I will do, I will make a four-way valve here. I'll put it, say, in the middle here, and all the piping between the two coils and the compressor will be connected through this four-way valve. Okay. So with some cooling, I will connect the inlet, the outlet of the evaporator to the inlet of the compressor as a cycle, right? But when I press heat, I have actually a small solenoid motor that will rotate the valve and will switch the connection. It will make the outlet of the, or this connection that was of the evaporator or this coil, it will connect it to the outlet of the compressor and it will revert the connection here, right? Okay. So this coil will work as evaporator that is outside, and it will take heat from outside at low temperature. And this coil will work now as a condenser. Okay. Right? Now, if we look, remember first law by Dr. Hunter gave that energy is conserved. So energy into the cycle should equal to the energy out of the cycle, isn't it? So what is the energy in this cycle? As you said, the electricity coming to the compressor, this is inlet, right?
Yes.
And the heat absorbed in the evaporator, this is inlet, right? Okay. These two should sum up and equal to the heat out from the condenser.
Yes.
Right? Now, do you know something called COP, coefficient of performance of air conditioners units or refrigeration units? You see the energy label with the stars?
Okay.
Yes. This gives you how much heat for cooling divided by the work of the compressor. This is what you really want. In summer, you need how much heat absorbed in the cooler or the evaporator divided by the work you paid from electricity, right?
Right.
This is in summer. In winter, you need how much heat coming from the condenser because this now will act as a condenser and it will heat your house. How much heat come to you divided by the electricity coming in the compressor, right or wrong?
All right.
Usually now the COP, minimum COP in US and maybe coming in Saudi Arabia also, that the minimum COP or ratio of Q cooling over work compressor is 3:1. And for heating, it should be 4:1. This means what? If you need 4 kilowatt heating in your house, you lose how many kilowatt electricity? 4:1 mean 1.
1.
If you need to heat your house by 4 kilowatt, so you with using this heat pump cycle, you will take from electricity 1 and you will heat your house by 4 kilowatt. The 3 kilowatt come from where? Is here in this example coming from the earth or coming from the air, natural air. If you have instead of this water loop that connect or couple the evaporator to the earth, you have a fan that makes the outside air circulate about, around your evaporator, right? Here we have a loop that couple the heat transfer between the coil and the ground. That's what we call this ground coupled heat exchanger, ground coupled heat exchanger.
Mhm.
Now you take 3 kilowatt free from the earth or from the atmosphere, and you pay from electricity 1 kilowatt that has a price, and you take for heating 4 kilowatt, right?
Yes.
Now, if you are heating by electric heater, and you need in your house heating of 4 kilowatt,
Yes.
how much electricity you will take from the utility?
From the utility, given the same factor 4:1.
No, I am talking now about electric heater, direct electric heater.
I'll use
Not
the 4 kilowatt.
4 kilowatt or little more.
Yes.
Of the efficiency of the electric heater or whatever losses in the wires. Huh? So
Yes.
let us say 100%, you will use 4 kilowatt.
Yes.
Now, if you run your electric heater about 3,000 hours a year, that is the winter season, let us say it's 3,000 hours a year.
Yes.
So how many kilowatt hour you will
12,000.
use?
12,000. 12,000.
12,000 kilowatt hour if you use an electric heater.
Yes.
But if you use this heat pump,
If I use the one with the geothermal,
or heat pump concept, either geothermal or even from air to air.
I will use 3,000 only.
So isn't it energy saving here?
Yes, yeah. I got the idea. It will save the conventional energy that we get.
Right. Is it clear enough now?
Yes, 100%.
Right. Now, let me tell you something in the cooling. Now you understand the idea of heat pumps. Either I used here, the evaporator is interacting with the air through a fan or through this ground loop heat exchanger. It doesn't matter. But what happened? The ground loop heat exchanger, you are actually circulating water or so. The heat transfer of liquid is much higher than heat transfer with gases. So when you have the interaction heat transfer between the refrigerant and the air is not efficient as the heat transfer when you have liquid around your refrigerant, right? So this is more efficient in heat transfer. The second important thing for cooling purpose, you have the condenser actually dumping the heat in the summer to the air at 45 degree. At 45 degree, right? Now, the COP for cooling is T low over T high minus T low as the ideal. Yani this is the limit for us. Just I'm taking it as an example. So this is Carnot refrigeration cycle. For cooling, the maximum efficiency is, or COP, coefficient of performance, is T low over T high minus T low. So the coefficient of performance, which is the ratio of the cooling amount over the work by the compressor, is T low over T high minus T low. So the higher the T low, what happened to the COP? T low will go down, T low, when it is high, then the COP is getting low, isn't it? Or so you need to more work to absorb this heat from your surrounding. This is normally. Now, let us think about this window type. Now, this condenser dump the heat where? To the air outside, isn't it? Hello?
Yes, doctor.
Now, when you cool the condenser with the cold water, it will condensate faster, or when you cool it with a fan with air that is at 45 degrees. Now you have two options, either to cool the condenser of your window type AC by air and a fan, right? The air is at 45 degrees in summer. But if you take underground water that is at about 30 degrees and you have a small pump to circulate the water around your condenser, of course you need to make modification in the condenser shape or designed to use water, the condenser, which one will cool faster?
The water.
That is cooled with air or the cooled with water?
With water.
With water. Great. Actually, this, if we think about the air conditioning unit, compare it with the human body, the compressor will be like our heart. And the condenser will be like the lung. If the condenser is full of gases, this represents resistance for the compressor to push more gas inside it, right? But if the condenser, the gas in it condensate fast to convert to liquid, it will leave its pipe free to receive more gas from the compressor, right? Who is following? Nobody is following?
Yes,
doctor.
No, we are following this.
So actually the condenser, as I said, is the lung of the air conditioning unit. If the gas coming to it at high pressure, high temperature, condensate fast, so always its pipe, because the liquid volume is very small to the gas, so its pipe always will be free to receive more gas from the compressor. So the compressor will find low resistance for it to push the gas inside the pipe of the condenser. So the compressor will not consume much work, okay? But if the condenser is not cooled enough or quickly enough, the gas will take more time to condensate, and always the pipes of the condenser will be full of gases representing resistance or load on the compressor to push more gas in it. You agree with me?
Yes.
We agree.
Right. And then if I cool the condenser with low temperature liquid, first of all, if I use liquid, then heat transfer coefficient is higher. Second, if I use low temperature, so I dump the heat easily and I condensate faster the gas in the condenser. Let me give you a quick example. I had a project team of a student and senior project about air conditioning and efficiency and this and that. I took them to the AC workshop in our university. Actually, in the workshop, it is air conditioned. The workshop itself is air conditioned. So there was one AC unit under maintenance put on a table in this workshop. It was open, the casing was open. I was showing the student, I want to show the students the coils, the condensers, the evaporators, the throttling valve, the compressor, the internal fans that circulate the air over the evaporator and over the condenser and this and that. Actually, there was one nice gentleman, a technician there, very senior one. And we asked him to help us to measure the power or the amperometer. This amperometer, that is a clamp amperometer. You put the wire inside the clamp and turn the meter on. It gives you the amps or power or something passing through this wire. You understand this? You know it, right? The clamp amperometer. So what this gentleman did, he turned it on the AC. Of course, the compressor worked and the fan on the condenser and evaporator worked. Then he measured the amps to the compressor. It was, I remember, 6.5 amps, right? So somehow, while he is working, so he switched off the fan on the condenser. He switched off the fan that circulate the air around the condenser. What happened, do you think?
Current increase?
The current increase. The current quickly moved from 6.5789. Oh, so in fraction of a second, it reaches 15 amps and the compressor tripped off. What was the change? He just switched off the fan that circulate the air over the condenser. This means there is not enough cooling to the condenser. This represents a lot of resistance to the compressor, so it needed more power. It needed to suck more amps from the utility. It tried to take more amps to be able to rotate. Otherwise, it's not able to rotate because the gas is resisting the flow. So what happened? The amps shoot up to 15, and due to protection of the compressor, its protection fuse tripped it off. So this gives you idea how the cooling of the condenser is very crucial to the operation of air conditioning system. So if you cool the condenser well, you have less work in the compressor. If you don't cool it well, you have high power in the compressor. So the consumption at the end depends on the ambient condition, how you are cooling your condenser. If you cool it well with low temperature source or sink, then you pay more work or less work. When you cool it well, you pay less work. So this is the idea of geothermal application in air conditioning, in heat pump application or air cooling application. Let us focus on the cooling. Actually, when we have cooling our AC unit by air, we consume more power, but if we cool it with water, we consume less power. That's why in central air conditioning, always you see cooling tower. The cooling tower actually is cooling the water. This water is cooling the condenser. And you have a loop that cool the condenser by the cooling tower, right? To cool the water that cool the condenser of the compressor. I'm talking about central air conditioning that is 1,000 ton refrigerant compared to 1 ton or 2 ton of your window type. So in the university, you have many central air conditioning system with many cooling towers. Now, in a place like a Rashid Mall or any big mall, when you have a central air conditioning and you are cooling it with a cooling tower, the cooling tower need a ground to build on it and take a space, isn't it? Right? In addition to the cost of building the cooling tower that cool the water, and this water will cool the condenser of your AC unit. So this area or ground in an area like Rashid Mall or so, if you have a shop on it, you can rent it with more money, isn't it? So what is the idea is to have, instead of the cooling loop of water between the cooling tower and the condenser, we have underground well where we dump the water down in the well and cool it in the ground and bring it back to the cool the condenser. So you have your arrangement of cooling the water that cool your condenser now underground. So at the surface, you can have a shop, you can rent it with more money. And even so, actually the cooling tower, what if the temperature of the air is 45, the cooling tower can cool the water up to 33, 35, 36, depending on what is the humidity ratio in the air. If you have relative humidity high, you cannot cool much the cooling water in the cooling tower because there is no enough evaporation. But in the underground, already you can cool the water this 12 degrees under the ground. So let me now, with this little introduction, start talking about types of geothermal ground heat exchanger, how much we can dump the heat in winter. In summer, we dump the heat down. In winter, we can reverse our air conditioning cycle and take the heat from the ground. But the concept of cooling, especially air conditioning for cooling, do you know why now geothermal can introduce a solution to reduce the power in the compressor?
Yes.
By cooling our condenser by water, and this water we can cooling down in the ground. Because why? Because the temperature in the ground always almost constant. If you go down here, you see this graph from some European country, but we have similar one I put some papers, I put a link in Blackboard that have some of our research paper on geothermal heat pump, coupled heat pump. Actually, they call it ground source heat pump, especially if we need to use the heat from the pump, or more general ground coupled heat pump, coupled because we link our coil to the ground by a loop heat exchanger. Ground coupled heat exchanger. So ground couple is more general. Ground source if I'm using heating for heating, as in the example I show, as in Europe or North America. Here usually if you see on the surface, the temperature of the air vary from summer to winter. But few meters down the surface of the earth, you will find the temperature almost constant. You see here, after 10 meters down, the temperature almost constant around 6 degrees. In our area, it is fixed around 32 degrees. I have this measurement. A measurement is, we reported in one of the papers that you can see it in geothermics, I think. I put about 4 or 5 papers from previous work. We have done it here in KFPM. I put the paper for your reference. You don't need to read it, but I want you to understand the concept that the ground temperature about 10 meters under the ground, the temperature is almost constant in summer and winter. It doesn't change, but at the top or the surface, even during the day, the temperature of the air vary from day to night and from summer to winter. But underground is almost fixed. As I said, the air in summer here in this area is around 45 to 49 degrees, but underground the temperature is about 30 to 32 degrees, right? So if in a summer day, I want to cool my condenser by the atmospheric air, I need to use a fan and I need to use a very large heat exchanger in size. And again, the work of the compressor will be high because the temperature I need to dump the heat to it is 45. I need to be above it by about 10 to 15 degrees. The compressor should work up to 60 degrees. But if I am cooling with the liquid water, the heat transfer coefficient better, so the area of the heat exchanger size is less, and I am using my compressor should dump the heat at 30, so my compressor need to work to raise the temperature up to 40. So it will not need to do more work. That's why the COP will be high. For the same cooling, I use less work in the compressor. And if I am using less work in the compressor, then I pay less electricity, I burn less fuel. Now, could I answer the question raised at the beginning? What is the relation between air conditioning and geothermal and sustainability? Is this answers the question?
Yes, Doctor. I raised the question. I feel it's, yeah. Now
very clear now, right? Okay.
Yes.
I'll just give you idea about the different type of the ground coupled heat exchanger. Here, this is our AC machine. Now it is working as heating, take heat from the ground in winter and emit heat to the house. Here in summer, we reverse the cycle, and now this loop is dealing with the coil that work as evaporator now. Sorry, as a condenser. Here it deals with the coil that work as evaporator in winter, but this same coil will work as a condenser. I'm talking about the coil, this coil. This coil can work as evaporator in winter. It take heat here and dump it to this. And in summer, we reverse the connection. So we'll have here, this will be the evaporator and this will be the condenser. We dump the heat down. So this is one vertical type, but we might have the heat exchanger coupled to the ground. Since we said 10 meter, this usually I need up to 10 meter or even sometimes 5 meter if you have a villa like this. Inshallah, all of you will have with the good backyard or front yard. You can have this loop that have the water that cool your cool or heat the coil is a connection with the coil in your air conditioning system. You can have it horizontal in shape like this, so you don't need much money to drill a deep well because drilling cost is very high. So the drill, this is called vertical loop heat exchanger. This is horizontal. This is called the slinky. The difference between each one of them, the vertical one, you can go deep up to 100 meters or so. It will take less space, but it will take a lot of cost to drill, because drilling here in Saudi Arabia is very costly. Especially most of drilling companies, they put their prices for the oil companies. Okay, but now maybe drilling water pumps or something make the cost less, but it's still very costly. But horizontal, you need only excavation. You need to just dig little, and the digging equipment is not expensive like drilling equipment. So the cost for horizontal wells or slinky well coils is less. But the area here, you need an area. Imagine you have your house only, you don't have a back yard or something. So it's better when you build the house, and of course you dig down to make the foundation, especially if you have tall building. So you can install the vertical loop during the construction of the house, and you don't need this, backyard. But if you have, so better to do this. But slinky take less size, less area, because it's like a serpentine here compared to this U-tube loop. These are different type. We have sometimes open loop if we have aquifer near the house, so you can dump the hot water here into the reservoir and then take the cold water, since this will be mixed with a big reservoir. Actually, we built one experiment here in KFPM 10 years back or 12 years back. We built one. And actually, the maintenance director came and he insisted not to dump water here. We made sure that we show him that we have this type, that is the U-tube. So we don't dump any water inside. It's a closed loop. The hot water will come down, lose its heat to the ground, and then we take it back as cold water. Actually, we were pumping water here at 45 and we take it out at 32 to cool our condenser at 32. And the efficiency or improvement in the performance was 35%, around 35% saving in the energy. This experimental work, we have done it by ourselves, but the drilling cost was very high. So it was not feasible economically due to the cost of drilling. And we used the closed loop because this was the aquifer of water used by the university. So the maintenance wanted not to contaminate the aquifer. But here, if you have a saline aquifer, or you guarantee no contamination, or it is your house, you can have the open loop. Of course, it might be cheaper, but sometimes you have even underground water that is flowing. It will take the heat and travel. But if you have a rocky place, so with time in summer, you dump the heat down in the ground, and in winter you suck the heat. This is if you use the heat pump. But usually in our places, the summer season is much longer than the winter season. And also Q high is always higher than Q low. So using the heat pump with the rocky place always will have the possibility that it will not work after a longer time, 10 years, 15 years. It depends on the heat transfer characteristics in the ground, because you dump heat more than you suck the heat in winter. Or some people use it only for cooling. We don't have winter season really. So if you keep dumping the heat and the heat is not dissipated around your coil, then the temperature of the ground may rise up over years. So the solution to use heat pump, that you dump heat in summer and take heat in winter, so to try to balance the temperature of the ground near your house not to increase much. These are different construction of horizontal types. You can have a trench with one pipe like this one layer, one layer here. Or you might have different layer above each other with distance, of course, like this. Anyway, you can have different arrangement. For vertical also, you can have different arrangement. Actually, this is the main component. This is the ground coupled heat exchanger. This is our AC machine that is connected to a coil. This coil might act as evaporator in winter or condenser in summer, depend on how I press the reverse button for cooling or heating. And of course, this air that is circulated in the air in the house, this is a supply air and this is the return. Actually, this is again repeated, this is a heat pump heating. Actually, we have one EAS software that we developed with one of our students at the time, Dr. Sharqawi, one for designing the heat exchanger, how much is the diameter, how much is the length that we need to dump heat, for example. We have two. One is the design is the rating. The rating is, the design is that we say that we need, for example, 10 ton. Let us say the ground properties. These are input data that we say this is the outer temperature. Let us say if I wrote here, instead of this, I wrote 49, then I'll see how this dimension and the cooling capacity will it change. I should say, and I don't know why it didn't work. Maybe this is high. Yeah. Let me make it 30 only. Oh, it doesn't work. ES is not working outside the building. Sorry for that. Yeah, it's the same ES program, only used. Okay, خلاص. But anyway, we developed software to make the design of a vertical loop. Now for deep geothermal, I want to go faster here to give you the concept how I use the power or heat in the ground, trapped in the ground, to generate power. Is there any question in geothermal, how it is related to air conditioning, how I can use it to make my AC unit perform better or use less power from the compressor to give me the same cooling or heating effects? How better is using the heat pump rather than electric heater? Is this clear? These concepts are clear? Hello?
Yes, Doctor.
Right. Now, as you know, if you look to the Earth's structure, the surface crust of the Earth is have the temperature of the surface. But when you go deep and deep, you will find maybe the core of the Earth is at 6,000 degrees Celsius, like the surface of the sun. I think our planet is part of the sun, but the core is very hot. And when we go to the surface, we have the normal temperature. So if we dig up to here, 1 kilometer, 2 kilometer, we will find the temperature, as we said, for 10 meters, the temperature is almost constant around here in this area, 32 degree or something. In Europe, it is 6 degree, average between minus and plus at the surface during winter and summer. But actually, if we dig more, if we drill more, like these oil wells can reach 1,000 meter, 2,000 meter, I mean, 2 kilometers, 3 kilometers down this to find the oil. At that depth, the temperature is high. So in some places you can either you have hot aquifer down, so you just drill deep, then you get hot water or even sometimes steam come out. In some places it is these hot springs are available, like in Harra near Medina and Al-Lis and Jazan. You do have the hot water even coming up. So just to preview the geothermal application, we have the shallow geothermal technology that is using the ground couple technology. We can use this for air conditioning application, for heating in winter and cooling in summer. For deep geothermal, we need the deep geothermal source. We need the drilling. We need the production and enhanced. So I'll tell you what is enhanced geothermal source. But this is the mainly, we have shallow thermal and deep geothermal. Actually, this lecture I prepared for CACAIR a few months back. So the energy saving, as I said, we used for air conditioning and improve the performance by about only 1%. Imagine, you don't imagine how much energy you are going to save in electricity in Saudi Arabia if we look to air conditioning that consume 55 of all electricity we produced. Now, this is some structure from geological people they give to us. Now, if you drill down, you'll find here some hot rock down. You might find some water streams or liquids that have natural convection. Sometimes it is all rocky places. Okay, you can build actually a power plant. If you can see here, these are pumps that circulate the water down to the ground and then take steam. And this is the cooling tower that cool the condenser of the power plant. You know, usually geothermal is linked to Rankine cycle, since in some places you have hot aquifer deep in the ground. So you can dig and you find steam and take it to rotate a steam turbine, then condense it to dump it back, or you throw out the steam to the sun. But this is Rankine cycle, and this is the cooling tower. You can see to cool the condenser of the Rankine cycle. So what are the classification of power plant, geothermal power plant? We have dry steam plants, flash power plant, binary, geothermal, all flash plus binary. Each one will give a quick explanation what it is. The dry steam, you just take the steam, dig down in the ground. You maybe 2 kilometers down or 3 kilometers down, you will find the steam coming. Then you take here, if the steam coming with any liquid, due to the fast drafting of the steam, you separate the steam, and then you have eliminator to eliminate any droplet liquids. Then you take this steam, usually it is superheated or dry steam, run the turbine and exit from the turbine. You can see here the steam coming out. These are steam, not a smoke. This is a steam coming out. You use that and throw it away. You take it from the ground and you throw it away. This has advantage that it's a simple cycle. You just have the connection to eliminate any liquid, not to hurt the turbine, and the exhaust to the atmosphere. You have only a turbine and plumbing. So what is the cost? Is the drilling and the turbine cost, and of course operation. But the steam coming from the ground, you pump it, under its pressure going outside the turbine. The disadvantage, if this aquifer that is underground is contaminated with radiative material or whatever, what type of contamination in the under the ground, maybe you have some chemicals, you have any poison material, then it might harm the environment. If it is not harmful, khalas, you get loose. But with time, this water ground will finish. So sometimes you need to condensate this water and return it back to your reservoir because the rocks are hot down. So you want to sustain this geothermal source for longer time. Why not to condensate this steam after the turbine and return it back? And this is what happened. This modification, the steam here after the turbine, you instead of throwing it to the air, you buy a condenser, shell and tube condenser, and you cool it by a cooling tower, especially if you are in desert, you don't have the Gulf to cool by water like we have here on the Gulf and Azizia power plant or Ghazlan, we cool it by water, seawater, and in Jeddah. But here, if you are in Riyadh or in Medina, you can build a cooling tower. And you know the concept of cooling tower, that you take the water here, push it as a shower, and then suck the air by a fan. Then the cold water will condensate and you can inject it back. I mean, from the condenser, you can take this and inject it back to the aquifer from which, so you have, this is the geothermal production well, and you have re-injection. So this is to keep the water instead of losing it. We do have another type of cycle that is mainly based on Rankine cycle also. It is called the flash type, where actually you might have hot water coming. So when this hot water coming at high pressure, you introduce this to a flash tank where the pressure go down. Then if you have hot water at high pressure, high temperature, you introduce it to low pressure room. So flash evaporation will happen. So the liquid water will be heavy and go down as the blue part here, and you can take it back to the reservoir by injecting well. And the hot is the steam, you can take it to operate your turbine. Okay.
Doctor, what is the use of the ball valve here?
Whatever the details here is
just general يعني.
Yeah, it's a valve, it's a control issue, because you need to control how much of steam is coming to your turbine. You don't need to actually put here, you see here the steam coming from this pipe. You put the pipe at the top and then steam only will come here. Liquid will be coming here. So steam here should come through a valve. You can open it, you can close it, you can separate if you need to omit any maintenance. But this are a lot of details. You cannot go through it, right? It's actually big plant. You have seen the picture. But here we are introducing the concept. Who was asking about thermodynamics? Thermodynamics is everywhere, actually. As I said, engineer is the one who converts science into technology. Because without knowing the science, you cannot develop a technology. This is a period here. So you should know what are the basics to be able to develop it more and more. Right. Now, this is another details of the flash cycle, where you have hot water, not steam coming from the ground. It gives you hot water. Of course, you can suck it using a pump, or it is coming at high pressure and you help it with a pump. With the flash, you can make the flash in 2 steps and guarantee here you have dry steam, but you condensate it back and inject it, as we said. We have other type that, as I said, if the water in the aquifer is contaminated, we know in some places the ground have some radioactive material. So maybe the water you are using is contaminated with radiation. So you can make heat exchanger that you have the water in a closed loop. You can pump it down and you keep circulating. Take the heat here in something like the boiler or the heat exchanger. And then this Rankine cycle has a closed loop water that is pure water, like any Rankine cycle. Actually here, if the source of the geothermal source doesn't have temperature up to 300 degrees, that's usually the case, that if you have only a dig to not very deep, you have temperature around 150, 130 degrees. So you can use different fluid here. Instead of the water, you can use the organic fluid that boil at lower temperature compared to the water. Since the organic fluid is not going to be pumped down, you have the heat exchanger, so you can use the groundwater as a source of heat, right? Circulated in this loop, geothermal loop. And you have the working fluid in organic Rankine cycle. You can use any fluid other than water that boil under a temperature below that of water. So we can use here CO2, we can use any other organic fluid. And of course, we cool it, we have the heat source here in the boiler or evaporator, then the turbine, then the condenser. Of course, the turbine rotates the electric generator, and the condenser, we can cool it by external water coming from the sea if we are close to the sea, or a special loop of cooling water from cooling tower. Okay, since we introduce here any fluid, we can use binary fluid like ammonia solution and we use what we call binary fluids. There are many ways now. You can see this is a geothermal plant that have here the pumps that circulate the water down, and we take it to whatever heat exchanger or directly to the turbine. It depends on the nature of the water we have, but it is not a simple cycle. It is like any power plant cycle is very complicated. This is just giving you idea what are the different technologies. Dry steam is 24%, that you take steam from the ground directly and you clean any liquid water from it, separated, and take the dry steam to the turbine. If you have a flash, single flash, if you have water at high pressure and you take this water to a tank of relatively low pressure, then since it is hot at high pressure, then flash evaporation, the steam will be at the top of the tank of separation tank and liquid water at the down. Then single flash is very common because usually you might have high water at high pressure, high temperature down rather than steam. Then this is 42%. Double flash, if you do the flash evaporation in 2 stages, then 21%. If you have binary fluid, like as I said, ammonia solution, which is ammonia and water in what is called the Kalina cycle, it's sort of modification of Rankine cycle. Then you have what we call back pressure type, this 4%. These are the technologies used in geothermal. Efficiency of geothermal for binary system is 7.5, for flash evaporation is about 11%. If we think you are saying this is a low efficiency, but the source is free, right? And this is the net efficiency. You take work from free source. You don't burn fuel. You are using the energy stored in the ground, but of course it might have a lifetime also because you are taking the heat from the ground. This is just a comparison of efficiency of different thermal cycles depending on the temperature. Like if you have the combined cycle efficiency, it is in the range of 50% or above. This is steam Rankine cycle efficiency in the range of also around 50. Internal combustion engine, geothermal application, ocean thermal application. Again, this is types of how you make the digging for enhanced engineering geothermal sources. I mean, enhanced geothermal, this when you have a rocky place and you want to inject water to get heat from the rock and you bump it up. Usually when you have the rock is from very solid, you need to make cracks in the rock in order to give a chance. So when you inject the water down, it penetrate between the cracks and then get as much heat as possible. You suck it from the production. This hot is the suction where you have hot water, and this is the injection when you inject cold water. Actually creating the cracks and going deep for drilling and using horizontal drilling. These are technology that really has a lot of development, and it's a very costly technology, and people work together, people from geology, from earth science, from thermodynamics, from engineering, civil engineering, mechanical engineering, electric engineering. They work together to build such a plant. Regardless of your background, of course, each one of these engineers should know what is going on in the plant, what we need. I mean, this geology engineer should understand what the mechanical engineer needs. And the mechanical engineer and geology engineer should understand what is the electric engineer needs. In order to be able to design and build such a plant, all work as a team. At least each one knows the minimum required information, but each one know deep what is his major or what is his specialty. So if you are taking now master degree in energy and sustainable energy, I think of course all of you will be focused in one line, but he should also, if you work as a team, you are 22% or 21, all of you should know the minimum information when you work together You have the same language, you have the same background, you have the same ground each one stand on, but each one will know more in one subject compared to the others. But the minimum information should be the same for all. To build a geothermal plant, of course, you need a preliminary survey. You need to decide where I want to put my plant. You need exploration. You decided, oh, in south there is more potential for geothermal, but where in south? In Jizan, in Lays, in Medina, near Medina, in Harrat? What type of technology? We need to explore. You need to make a testing well. You need to drill a well, one well to take the temperature distribution, know what is the temperature gradient. How much you need to dig. If you need, for example, in a place that temperature gradient is 10 degrees per kilometer, the temperature increase in 10 degrees per kilometer. So how much to go? You need to go down. How much depths, you need to dig. Then the project planning, revise it, field development, maybe you need to change something because of the location. You decided the construction, how much, the startup and commissioning, operation and maintenance, all this you need to make plans for it. These are an example of the cost or estimate on this indicate cost for geothermal development of 50 megawatt geothermal in US $1 million. For each item that we said, the preliminary survey, how much it cost, might cost $1 million, up to 2 million, up to 5. The exploration is to go and explore the place, test the drilling. You see the drilling can cost $30 million out of 50 million, the total cost. Feasibility study and drilling cost, and you see drilling 20 boreholes can cost 145 to 100 million. This is for 50 megawatt. You need how many? 20 boreholes that cost about 100. So each borehole can cost $5 million, right? This is just the example. This is total installation cost for proposed 100 megawatt geothermal plant in Indonesia. This is how is the distribution. This is the power plant itself is 42% of the total cost, 13 for steam field development, for injection well is 4%, test well is 1%, production well is 15%. One can tell me why the production well is more costly than the injection well? If we inject the water, it is cold, but production will always have high temperature. So the material of the well coating and other thing is different. So I will let you enjoy. This is one of the drilling facility. Again, drilling cost, how it vary with depths. So this is the drilling technologies, and these are general information. I will not go through the technical requirements, but this is just also some numbers about the pressure. So I want to stop actually to avoid getting you bored. And I want to know if you have any questions, please.
Yeah, Doctor, this is Rakan. Actually, we have arranged with the professors for the other 2 classes for the upcoming tests and quizzes. And we have organized them so that each week we have a specific subject to focus on so that we will be prepared for the tests and quizzes. Yes. Now, the issue is that there is an issue with this class and another class that they are in conflict. And we are seeking your support to postpone the test for 1 week only so that we will have enough time focusing only on this 542 class.
Right. Actually, for me, I finished module 4, 5, and 6. I will try to post the homework today. Of course, I posted maybe 60, 70% of the homework already and we discussed all of the problems in the help session. So some of you already, I think, made the homework or went through the help session. What I will do, I will try to give the homework again, but for different number for each student, depending on his ID. So I'll try to post the homework today or maximum tomorrow, so that each one will get training to different numbers. But the concept of solution we have discussed already, or we have discussed it either in the help session, also in the example in the lectures. Dr. Antar was saying that next week you will have this module 7 by Dr. Nakfi, I think. He will give the nuclear. So next week will be off, right?
Yes.
Then the week after you will start the nuclear, and this will be November 7, I think.
No,
actually in October 30, we will have, that weekend, we will have classes. And then on Saturday, on that weekend, we will be having a test for 540 class. So for this reason, we're just asking to postpone our test for this class to be not on October 31st, but the week after.
On 7th?
On the 7th, yes.
Yeah.
It's okay. I think Dr. Hunter was saying something similar.
That's great.
So, but I will post the homework from now, so you can practice and prepare yourself.
Great, great.
The exam will be similar to the homework problems, but again, as Dr. Hunter did, each student will have a different number, same question, but with different numbers.
No problem. Shukran, Doctor.
I'll see how I will make the question. I mean, for each one, we'll have different exam or a paper and send it by email as Dr. Hunter did, or I will do, I'll make one exam and I'll put a table. I mean, I give the problem with variables like mass flow rate M and pressure B, right? Temperature T. Then I put a table down with each student ID or name. I'll put what is M, what is pressure, what is temperature. So that I will have one exam paper, put it in Blackboard, all of you download it, but you take the variable from the table under each problem to see your values that you are going to use. Is this fair enough?
Yes.
Fair enough, Doctor.
Okay.
And instead of sending each one exam and we follow if you get it or not, and also disclosing the exam, we need to disclose it at the same time. I think I put it through Blackboard to one sheet or so, one file. So all of you can browse it, but everyone will use different numbers.
Great, great. Allah يعطيك العافية, Doctor.
وإياكم إن شاء الله. Thank you very much.
شكرا.
Our exam, Doctor, on the 7th, huh?
نعم.
آخر homework أعطيتنا إياه.
Man. I will post, as I said, this is a draft. It is not the final homework. When I post it, I will post the final draft. I will announce the date also. I will